Okay, so sinhx is equal to 1/2 e to the x minus e to the minus x, and we want to find arcsinhx, which is the inverse of sinhx. So we find inverses in the exact same way we find inverses for all functions. We rearrange, to bear in mind sinhx is a function of x, so it's like f of x. We rearrange for x, and then we substitute back in x instead of y. So we set y is equal to sinhx, so y is equal to 1/2 e to the x minus e to the minus x. Multiply that by 2, we get 2y is equal to e to the x minus e to the minus x. Now the trick here is we multiply this whole equation through by e to the x, and you'll see why in a minute. So 2y e to the x is equal to e to the 2x minus 1, because e to the x multiplied by e to the minus x is e to the 0, which is 1. Now, if we rearrange this, so all the terms are on the same side, so we'll get e to the 2x minus 2y e to the x minus 1 equals 0. That's a quadratic in e to the x. Okay, because you can see e to the 2x is e to the x squared, and we have e to the x, and we have a constant term. So we can actually use the quadratic formula to find e to the x here, and hopefully you can see where this is going, because that's the way we can find x. So using the quadratic formula, we get e to the x is equal to minus b, so 2y plus or minus, and then we square this term here, so we get 4y squared minus 4 times minus 1, so that's plus 4. That's all over 2 times 1, so that's 2. We take out root 4 here, root 4 is 2, and then dividing by 2, so we get that y plus or minus the square root of y squared plus 1. If we take natural logs on both sides, okay, because that's the opposite of e to the x, we get x is equal to ln y plus or minus square root of y squared plus 1. But of course this doesn't make sense for inverse functions. Inverse functions have to be unique, and we can't have this plus or minus. So we've either done something wrong here, or this one of these isn't valid for some reason. And it actually turns out that if you think the modulus of y is always less than the square root of y squared plus 1, that's because the modulus of y, so the size of y, is equal to the square root of y squared, and like by definition. So if you think when we're subtracting the square root of y squared plus 1 from y, we're always going to get a negative argument inside ln, and the natural log's not defined in that region, so the actual function we get is x is equal to ln y plus square root of y squared plus 1. Okay, and so that's our inverse function. Arcsin of x is equal to ln x plus square root of x squared plus 1, and we would expect this, that we get this some involvement of the natural logarithm, because sin's a function of exponentials. Yeah, this is what we get. Notice that I haven't worried with a range of x values. That's because I didn't even check this, because I know what the graph looks like. I know that sinx is 1 to 1. Okay, so it's not like this inverse is only valid on a certain region of x values, because it's 1 to 1 everywhere, so that's fine. But if you want to try this exercise with cosx, you have to think cosx is not 1 to 1. So you do have to remember certain things about cosx, alright, and look at the region that the the inverse is valid. If enough people want, I will go over that, but for now we're just doing this because it gives you a nice general method. So yeah, that's it. And if you are to do that Koch exercise, the exercise works in a very similar way. You can use this quadratic trick, but yeah, you just have to be careful. So thank you very much for watching. Hopefully you've enjoyed the video. If you did, please like it. Really appreciate the support on the channel. And let me know anything you need covered in more detail, even if I've already done it before and you just want a longer video on it, or I'll miss something out, that's fine. But thank you for watching. Like I say, please subscribe to the channel for more maths content. I hope to see you in the next one.